All right, so welcome back to our lecture. We went through already how many lectures? 6 lectures, 6 out of 13, or 6 out of 11, if we don't count the last two. So we reviewed what we did mostly on the, or exclusively on the incompressible side, mostly with viscous flows, Stokes flows, exact solutions, and boundary layers. What we did in lecture number 7 and lecture number 8 was the package of 2 lectures, was to go into the whole potential flow theory, which is disjunct from this whole viscous flow theory. It's not Navier-Stokes anymore. It's flows where we neglect viscosity, or let's say we idealize the flow to be a flow without viscosity. And that led to the theory of potential flow, or ideal flow theory, as you will see it in certain books. We also saw that potential flow theory is applicable wherever the flow is irrotational or has zero viscosity. And typically, this is the case if we're going away from walls or away from objects. So, for example, of a wing of an airfoil, we'll have a little boundary layer on the surface of the wing, and outside this boundary layer, viscosity quickly drops to zero, exponentially fast, usually goes to zero, and we obtain a large field. Actually 99% of the flow field will be irrotational and can be described by potential flow theory, because there viscosity will not play a role. Keep in mind, there's also wakes behind objects. Wakes, we only introduce, well, somehow we introduced them a little bit when we look at flow separation, but then we will look at it again in the lecture on aerodynamics. That's 2 lectures later. In these wakes, they're also far away from the object, but their potential flow theory does not work, because in a wake, you usually have a lot of vorticity. You usually have turbulent flow, and their potential flow theory doesn't work, okay? But outside wakes, turbulent wakes, and outside the boundary layers, potential flow theory does a good job. And the equation that we have to solve there is remarkably simple. For the velocity potential phi, that's the typical variable, we just have to solve a Laplace equation. Laplace of the Laplacian of the potential phi must be equal to 0. And we also found that if the flow is irrotational, the same equation also holds for the stream function psi. And the stream function that we introduced in lecture number 2, flow kinematics. So it's not true for every stream function, but it's true for a stream function in irrotational flow. There it satisfies also a Laplace equation. And we saw that the streamlines which are isocontours of the stream functions are perpendicular to isocontours of the potential, of the velocity potential. Okay, isocontours of phi are perpendicular to isocontours of psi. So they give you like a pattern like that, or you see it, I think, on the next slide, where we have a few examples. For instance, here psi constant is a circle. So these are streamlines. So these are circular streamlines. So that describes a vortex in irrotational flow, and we saw that before. There is a vortex. It's the ideal vortex. That's a vortex where you have zero vorticity. It has the singularity in the middle. That's usually where the cylinder is sitting, that is rotating. And if you exchange the iso potential lines with the iso stream function lines, so the stream lines, you get this picture here. So these rays here become now streamlines, and the circles are now isopotential lines. And again, this is a solution of the potential flow equation. And this describes the source. Something comes out of a little source here, which is also singularity at the origin. And if you have a negative source, you have a sink. So the arrows go in the opposite direction, everything goes in here. And of course, here in the center, at the very center, mass conservation is not satisfied anymore. That's why the central point, the origin, is not part of the solution, but everything else is solution. We looked at this nice solution for stagnation point flow, or if you decide that this wall here, or sorry, this streamline here is also a wall, a vertical wall, then this is the solution for a flow in a corner, in a 90-degree corner. Remember that in potential flow theory, we had to let go of one of the boundary conditions at the walls. We could still ask for streamlines not to pass through the wall. The walls are still walls, they're not impermeable, but we had to let go of the so-called no-slip boundary condition. We had to allow a tangential velocity on the wall. This is not true for viscous flows, but in inviscid flows or in ideal flows, we allow a tangential velocity at the wall. In reality, there will be a thin boundary layer on top of this wall, or if we put a wall here on top of that. And if the Reynolds number is high enough, the thickness of the boundary layer will be very small, so small that we can even neglect it just for understanding the bulk flow. What else do we have on this slide? What is this here? This is the solution for a dipole. A dipole is something that you obtain if you put a source and a sink of equal strength, of equal opposite strength, just next to each other. So whatever comes out here is sucked in on the other side. And if you put them very, very close, actually infinitesimally close together, you obtain streamlines that look like circles. So whatever comes out here is sucked in the sink, and that is called a dipole. A source and a sink, these are monopoles, and two monopoles which cancel each other give you a dipole. If we take a monopole or a source and superimpose it with a parallel flow, a flow coming from left going to the right, we obtain a velocity, a flow solution that looks like that. It has one streamline which meets here, or a set of streamlines which meet here at this point S. This time it's not a separation point, this time it's a stagnation point. That's where the velocity of the oncoming flow goes to zero, it stagnates here. Zero velocity, with Bernoulli, we know zero velocity also means maximum pressure. And it accelerates again. And because streamlines can also be walls, we can consider this to be an object, a blunt-shaped object in a parallel flow. Oncoming flow, you can think of this as the leading edge of a wing, for instance. If we take a monopole, we get this configuration. If we take a dipole, we get this configuration. So with the monopole, this object here actually does not close. It just stays open, goes toward infinity. With the dipole, it's closed and it's even has the shape of a circle. Because we have this streamline here and we can compute the velocities here, we find again, we have a stagnation point here, a stagnation point on the opposite side, it's fully symmetric. And we have a maximum velocity here at the thickest point of this object, or at the highest point of the cylinder. And then we have a maximum velocity of 2u. If the oncoming velocity is u, we have exactly twice the velocity up here. We can again use Bernoulli to compute the pressures here, and we can look at the pressure profile. And because the pressure profile is perfectly symmetric, not only with respect to the x-axis, so above and below the x-axis, we have the same profile. So all the forces acting on the cylinder are balanced above and below. It's also the case with respect to the y-axis. So whatever is happening on the upstream side is also happening on the downstream side. Therefore, we get the counterintuitive result that the drag is 0. In a mathematical sense, it's a correct result for potential flow theory. In practice, we know that this result is completely useless. This tells us that potential flow theory is not good to compute drag forces. It's very good to compute streamlines and maybe pressure forces on the upstream side, but on the downstream side, it actually does a very bad job. We only learned in lecture number 9 or lecture number 10, I believe, on aerodynamics, that we obtain a wake here, we get flow separation here, and we have asymmetric pressure condition on the upstream and downstream side. That's where the drag is coming from. Plus, of course, the friction drag from the boundary layers, which is also neglected. What else did we do? We introduced the concept of circulation. We had the cylinder and we let it rotate, and this deformed the streamlines. Actually, if we have a rotation in clockwise direction, we have accelerated flow up here, and in clockwise direction, we get a decelerated flow down here. So we get a lower pressure because the velocity is accelerated. We have an even lower pressure here and a higher pressure there, which ends up in creating a lift force. Potential flow theory, as bad a job it does in terms of drag forces, as good a job it does in terms of lift forces. We get a remarkably simple result, the so-called Kutta-Joukowski lift theorem, which just says that the lift force is equal to the density of the fluid times the velocity of the object, or the velocity of the oncoming fluid, if you like, times gamma. And gamma is the circulation, and the circulation is simply computed as the integral of the velocities along a closed integration path going around the object, or if you like, along the surface of the object. That was one of the important results of potential flow theory, this Kutta-Joukowski lift theorem. What else did we do? We made an excursion to complex numbers, introduced a complex potential, which was maybe a bit confusing and very abstract, but at the end, if you understand what's going on, you see that it creates a beautiful, simple, unified theory, which combines potential functions and stream functions into a single complex valued function, and the derivative of this function gives you the velocity field, at least in 2D, as complex numbers. The real part is the u velocity, and the complex part is minus the v velocity. Yes. So this is what we did on potential flow theory. Let me put this on the blackboard now. Yes, so where does this go? It certainly will not go on the viscous part. Well, it's still incompressible. It's on the inviscid side. It is not the 1D Bernoulli. It is actually a new branch here. So let's put it here. Potential flow. which was only valid for irrotational flows. So the curl of the velocity field must be zero, otherwise it does not work. If that is the case, we get a Laplace equation for the velocity potential. And well, then we did a few more things like the circulation. Maybe let me mark it here. We introduced circulation. We introduced a bunch of fundamental solutions. We introduced the complex potential, which combines the velocity potential phi with the stream function psi. And what else do we do? Yeah, well, let's leave it at that. Huh? Just a few more things. But this was certainly a big block with a lot of theory, a lot of useful theory. That's what we had 2 lectures on it, lecture 7 and lecture number 8. Okay, and from that, what else do we need? Next important thing, or the one missing thing that we did not do yet, was turbulence. Turbulence is an extremely complex topic. Usually people take whole courses on turbulence or multiple courses on that. We only had 2 hours. We cannot do that much, but I hope I was at least able to give you the basic concept of turbulence to show you that a vortex by itself is not yet turbulence. We need not just fluctuations, we need a certain irregularity, we need a chaotic behavior. Maybe you remember this Lorentz attractor, how it all of a sudden, just with a certain, at that time there it was a Rayleigh number, but mostly it's a Reynolds number. We have a critical Reynolds number. If we surpass this Reynolds number, all of a sudden results become chaotic, or in fluid mechanics called turbulent. There's a lot of vorticity in turbulence. There's a lot of dissipation in turbulence. If you look at mass transport, for instance, you want to mix 2 substances in chemical engineering, or if you have combustion and you want to mix fluid, you want to mix fuel with air, then you want actually turbulence to create a good mixing. Mathematically, we introduced the concept of the Reynolds decomposition. Reynolds averaging, this ensemble average, we run the same experiment many times and average over the results of many instances of the same experiment. So we get an ensemble average, which is a mean flow. It's not a temporal or a spatial mean, it's an ensemble averaged mean flow, and with fluctuations. So we separate it into these capital U for the mean flow, the Reynolds average flow, and the lowercase u for the fluctuations around this mean, reformulated Navier-Stokes equations, and found equations which look almost like the original Navier-Stokes equations. Never mind, this term here is just a buoyancy term, which have to be used in the book that I copied this equation out of. But the real new term here is that one, the one marked in red, which is the average over the product of fluctuations in different directions. Ui times uj averaged. So it is actually a cross correlation or correlation, cross correlation of the fluctuation velocities. And that is a term which is usually not known. And for that, we need turbulence models. So if you run a CFD code like we did last week, and you know the flow is turbulent, you will in reality only solve for the mean flow, and you will need a turbulence model, to guess, if you like, what this term is. This term represents the non-described fluid structures, the unknown fluctuations. That's what many codes, not all codes, many CFD codes are doing when they say they do turbulent flow. In reality, it's called a RANS simulation, a Reynolds averaged Navier-Stokes solution. We also looked a bit at theory of homogeneous isotropic turbulence, like the prototypical turbulence. We saw that we can come up with the smallest scale that is present in turbulent flow, the Kolmogorov length scales. It's the whole Kolmogorov theory. We had some results on that. Maybe you remember this example we made with the blender, where you create turbulent flow with an electrically driven blender, and we could compute how small the smallest vortical structures are in that object. We looked at transition to turbulent flow, that we start off, an example of a boundary layer, with a laminar boundary layer, maybe here a Blasius boundary layer, and that the certain critical Reynolds number, we transition into a turbulent boundary. Remember, the Reynolds number based on the thickness of the boundary layer is increasing from left to right. Boundary layer is getting thicker and thicker. And if you formulate Reynolds with the boundary layer thickness, the Reynolds number gets higher. Here about you have the critical Reynolds number, and you go into a turbulent boundary layer, which happens to have a mean profile with a steeper velocity gradient at the wall. And we remember, shear stress at the wall is proportional to the velocity gradient. In that case, the mean velocity gradient. The mean shear stress is proportional to the mean velocity gradient, which is higher. Therefore, turbulent flows on average experience higher friction at walls. That's why aircraft engineers don't want turbulence on their airplanes, because it creates more drag. That's a simple point. We looked at what this means in terms of the drag coefficient. These are the drag coefficients we get for laminar flow, and then for certain range of Reynolds numbers, we have to transition from laminar to turbulent. And once we're sufficiently high with the Reynolds number, and down here it is the Reynolds number, we go into turbulent regime and have usually an elevated drag coefficient. So now let me put this on a blackboard as well. So turbulence is, well, we still look at incompressible flow. It's definitely a viscous phenomenon. You don't get turbulence without viscosity. It doesn't really have to do anything with Stokes flow. There will never be turbulence in Stokes flow because you have two small Reynolds numbers. It's certainly not an exact solution. No one ever came up with an exact solution for turbulence. Well, yeah, it has something to do with boundary layers, but in boundary layers, we only looked at the laminar versions of it. So let's put this here. That was our lecture on turbulence. See, our sketch becomes very crowded now in our diagram. Turbulence, that was lecture number 9 now. 6, 7, 8, 9, yes. That was lecture number 9. Okay, so let's stick with this picture now. So we have boundary layers, we have turbulence, and we have potential flow theory. And what we actually did in lecture number 10 is we pulled together all that we learned about turbulence, about potential flow theory, and about boundary layers into a lecture on aerodynamics. Sorry for the ugly writing. We can still read it. So really the lecture on aerodynamics, which was lecture number 10. It's really a combination of what we learned on boundary layers, what we learned on turbulence, what we learned on potential flow. This combines everything. And we used all that to understand what's going on in practice, not just in theory. What's going on in practice if we have a flow around an object like an airfoil? How we can generate lift and drag forces. Where does the drag force come from? Why does the drag force around a cylinder not look why is there a drag force, not a zero drag force as what potential flow theory predicted? That there's a wake which is often turbulent, that there's flow separation, that there are boundary layers which can be laminar or turbulent, which will affect the position or the location of the separation point. So this really combined all these little elements that we developed in the beginning, and we ended up with diagrams like these for different objects, which tell us what drag coefficients, or here friction coefficients, or lift coefficients look like. We made a few applications to sports ball aerodynamics, here a cricket ball, where we understood how, well, I actually don't know what they're called, pitchers probably, how pitchers use fluid mechanics, probably without really knowing it, but they use fluid mechanics, different locations of flow separation to create curved balls, or soccer player, tennis players, and so on. We also looked at a little bit of wing theory. We introduced a bit of the nomenclature terminology in wing theory. We looked at a certain family called the Yukovsky airfoils, which can be applied to potential flow theory. We looked at what's happening in stall, where a separation point is very early. We have separated flow and turbulent, usually turbulent recirculation zone. And we saw what this means in terms of lift coefficient, drag coefficient, and how we can plot this into a so-called polar plot of lift versus drag. There's some special points on it, like maximum lift, beyond which you very soon have the stall point. You have the optimal L/D ratio. You have the point where you have zero lift, and so on. So that was the whole lecture on aerodynamics. Now, my blackboard is almost full. There was one thing missing on this, or there's one thing missing on this blackboard, one thing we have not labeled yet, and it's on the very right. It's the whole theory of compressible flows. And even though it's just a small box on my blackboard, of course, it's a huge theory. Actually, it's an even bigger theory than a theory of incompressible flows. We did not touch it that much, well, only in one lecture. Well, first of all, because we have a limited amount of time available, but also because compressible flows will not be so important for you as biomedical engineers. Almost all flows that you have in biomedical flow systems will be incompressible flow. Nevertheless, we looked at compressible flow. We looked at a few basic results. we introduced the concept of the energy ellipse, which is relevant to adiabatic flows, where you can exchange, let's say, potential energy with kinetic energy. You can go into high Mach number supersonic configurations, subsonic configurations, stagnation configurations. You have the sonic configuration where the velocity is equal to the speed of sound. And then maybe in terms of practical application, the most relevant problem that we looked at was the Laval nozzle, which allows to create supersonic flow by going into a nozzle with subsonic flow, create a choked flow at the throat, Mach equal to 1, and then go into supersonic. And if we look at what's happening on this side with supersonic flow, usually or very often we get a situation where we have a flow discontinuity. This is a place where you have a so-called shock or Stoß in German. We looked at a little bit at the shock theory, at the Rankine-Goniot relations, and then we made some extensions to oblique shocks, detached shocks, and the opposite thing if you have an expansion, where you have an expansion fan, Prandtl-Meyer expansion fan. So this was lecture number 11. And instead of listing all the things that we did here, let me just list one result, which will be very, or maybe the most important result to you. And it's the result that compressibility becomes relevant if the Mach number is larger than 0.3. Or said in the opposite direction, if the Mach number is less than 0.3, which is the case in many applications, you can safely neglect compressible effects. So that is the big picture of what we did, the big picture of all the theory, how this is all connected. You find more or less the same plot here on Ilias. Just make sure the numbers are not correct. You have to exchange them with the yellow numbers that I put here, because that was from a different year where the schedule was slightly changed. So what else did we do? Let me just quickly finish. We also looked at experimental methods in fluid dynamics. Usually we would have visited that wind tunnel here. That's a wind tunnel at ETH Zurich, the large wind tunnel at ETH Zurich, built in 1934. We have looked at a few experiments, which hopefully would have given you some practical insight into the theory that we did here on the blackboard and the lectures on the blackboard. Well, we have exchanged that by an actual lecture on methods of fluid mechanics. I hope that was interesting anyway, and you learned something about the tools that the experimentalist has at hand. Lecture number 13, the one last week, was this little workshop, this interactive workshop on computational fluid dynamics, where Kai walked you through a few tutorials on COMSOL. It's important to me that you remember what advantages and disadvantages are, CFD versus experimental methods, that you keep in mind that one method does not do it all. You always need a healthy balance between the two methods. They both have their advantages and disadvantages, which are very often complementary. So by sensibly applying the right methods, you can get the full picture. Yes, well, let's not go into these details. So this pretty much closes everything that I wanted to do in terms of a review of the past 13 lectures. I would now like to give you some time to do the course evaluation. This is the email I received last night. that you should have received a link for the online evaluation. If you have not done that, well, please make yourself seen on the chat function. Otherwise, I would like to give you, what time is it? Yes, let's take a, well, I will take a break and you write the evaluation until 3 o'clock. And at 3 o'clock, we'll continue and I will talk about the exam. Okay, so I will just take a break and I'll talk to you again in 10 minutes. Okay, so let's continue with the lecture today. We have developed our review of this whole course of 13 lectures, and you should have time now, have had the time now to fill out your course evaluation. Let me close today, and let me close the whole lecture with a quick view at plug in over here. Yep. With a quick look at what we're going to do for the exam. Let me go back to the slides. So instead of having a written exam, as we typically have in this course, typically it's a written exam with 90 minutes for problems, large problems with many sub-questions. We're going to do an oral examination. As due to this whole COVID situation, it's going to be an oral examination via Zoom. And I want to show you this slide here regarding the organization of the exam. You either already have or soon will receive the dates of the exam. From what I know from the study administration, this will be either June 16, 17, or 25. It's not me who does this planning, it's just what I've been informed that this is how it will be. Yeah, as I said, it will be an online examination via Zoom. Each student will have 20 minutes allocated, and obviously you must have access to Zoom. You will receive via email a link to log in well beforehand, and I'm expecting you to have a few tools at hand during this exam, but I'll explain to you this in the next minute. So how does such an exam work? You join the Zoom meeting well ahead of your scheduled time, and there's a waiting room. And you wait in this virtual waiting room until we are admitting you to the actual examination room where we'll be interactive. So we meaning Kai and me, and the candidate. Kai is, well, actually I don't know the word in English, the Beisitzer of the exam. He will also take notes, and that's also a legal requirement to have just a third person present in an examination. Okay, so you will be admitted to the virtual examination room where the three of us will be seeing each other and be able to talk to each other. The first thing that will happen is that I will give you an assignment, a problem. I will show you essentially a slide on the shared screen with a sketch on it and a problem question. This will be a simple problem, will not be a large problem where you have to do a lot of math, but it will be a simple problem. And you will be given 5 minutes to prepare this problem. Now, obviously, these 5 minutes will not be enough to solve the problem in every detail. It's really just to give you some time to look at it, think about it, and start taking notes. So I'm expecting you to have pen and paper ready during this oral exam to take a look at what you see on the screen and start writing down a solution or outline a solution. Just prepare to talk with me after these 5 minutes about the solution. Because after these 5 minutes, I will ask you to take a photo of your notes. That's why you will need a mobile phone with you, and email me or WhatsApp chat or whatever. Email me the photo of what you have written. Then we'll put this on the screen, and then for the rest of the exam, we will talk about what you have written. So imagine, for instance, that you see when you join me at the examination room, I will show you, let's say, a picture of a pitot tube, and the question may be, how does a pitot tube work? You'll have 5 minutes to maybe draw some pictures on a piece of paper, maybe write down the Bernoulli equation, and just a few basic concepts. Just see what you can write down, how you can prepare. Upload your notes after 5 minutes, and then for the remaining 50 minutes, we will talk, the three of us, me, Kai, and you as a candidate, will talk about the solution of the pitot tube as a part of the examination. So it's not just what you write will be the outcome of the exam, it's really just an intermediate step, which gives you some time to think about the problem, to write down a few things. Okay, I hope this is more or less clear. You will get, before the exam, detailed written instructions by email. But what I can already tell you, this is more or less what it will work like, and you will be expected to be ready at that time with your laptop, with a camera, and pen and paper, and you should have somehow the technical ability to have a mobile phone with which you can take a photo of the sheet that you've written and send it to me. It's important that you can hand in something of paper. I will not accept something. I know a lot of you write on the tablet, which is maybe convenient, but in terms of the examination, I would like to have something on paper with a photo that is being sent to me. That has another, let's say, legal quality than something strictly electronic that can be pulled on from some other place. Okay, so this is a bit of the organization of the exam. I already gave you one example, like a pitot tube with the question, explain to me how pitot tube can be used to measure velocity. In general, what will you need to know? Well, in general, you will certainly need to understand which phenomena are relevant for a flow problem. And in order to do that, you need to be able to compute dimensionless numbers. Right? If I show you a flow problem, let's say a bacteria in a fluid, you should be able to come up with an explanation why this is a Stokes flow problem. You should be able to maybe write down in the first 5 minutes what the Reynolds number looks like and why this Reynolds number is much less than 1. Come up with a few numbers for it. You should be able to tell me, if I show you an airplane, why Stokes flow is not a good model for that, why you will have boundary layers, why you will have turbulent flow. You should be able to tell me what the Reynolds number is. if I show you an example of, let's say, a heart of an aorta, you should be able to tell me how you would compute the Wormsley number. I don't really care that much if you're able to give me exactly the right number for that. Of course, you're not expected to know what the exact size of an aorta is or what the exact viscosity of blood is. These 5 minutes are not an exercise in who is using Google the fastest. It's really an exercise whether you can grasp the concept that a Wormsley number is important, that a Reynolds number is important, what the basic flow solutions are, why this might adhere more to a Poiseuille solution, why this might adhere more to Wormsley flow solution. That's why I wrote here on the slide, it's more important to get the right order of magnitude than the exact value. It's more important to me that you know that the Reynolds number is much less than 1 than to know whether it's 0.0001 or 0.002. Certainly a very good preparation for the exam is to take a good look at homework assignments. The problems that we will solve will have the character of homework assignments. Just notice that there's a question on the chat. So is it allowed to look things up in those? Yes, absolutely. You're allowed to look up things. Huh? It's yeah, maybe I should have said that. The written exam is an open book, open notes exam. The way I do exams is that people can look up things. But of course, that also means if you don't know anything about anything and you expect that you can read up the whole topic in 5 minutes, well, then you're probably out of luck. Yeah? So being prepared for the exam does not mean that you know every formula by heart. Being prepared for the exam is that you know which formulas exist and where you can find them. And if you decide this formula is important, it's perfectly fine if you browse through your notes and look them up. It's not learning by heart whether there's a plus or a minus sign. It's learning by heart or by concept what the important effects are. Okay. So here's just an example from past years out of the written exam, which obviously is not that relevant anymore for the oral exam, but still, it just shows you the character of the questions that could be asked also during an oral exam. We have here a problem on aerodynamics. Problem A, the potential flow theory provides good estimates for the lift of an airfoil. Give the formula of the lift force. Right? That's the L equals rho times U times gamma. Right? That's what we just had on one of the slides before. Potential flow theory shows that lift requires circulation gamma. What is the criterion for determining the right amount of circulation on an airfoil? Well, those of you remember, they remember that it's the Kutta criterion that there should not be any flow around the trailing edge. Those who do not remember that, well, probably that's something you should learn in preparation for the exam. Problem B, potential flow theory fails to predict drag force. Discussion about that. This could be a very classical question during the oral exam that I will tell you, well, please explain to me, why do we not get a good prediction for drag force for potential flow theory? Then I would like you to hear talking about that. Maybe in the first 5 minutes, you could already write down a few ideas about it, or you develop them in the 15 minutes after that when you talk to me about this problem. Problem C, boundary layer of large parts of an airfoil can be described by the Faulkner-Scan boundary layers. Draw qualitatively the velocity profile of Faulkner-Scan boundary layers at location 1, 2, and 3. 1, 2, and 3. That's something that I could ask you to do in the first 5 minutes. And then in the continuing 15 minutes, we would talk about why you drew them one way or the other way. That's why I would like to have something in writing from you. If we're just talking, it's a bit difficult. We always need something some sketches, some writing. Yeah, and so on. You can take some time, and you have these slides. You can look at these problems. This is a typical character of questions that I am asking during exams. So with that, I believe this is my very last slide for today and for this whole lecture. So thanks again for attending and participating. It's been a bit of a difficult semester with, well, everything has changed. At the same time, I think, well, it's still been good, and I somehow enjoyed taping, recording my lectures, and yeah, I hope you learned something. So I would like to close here, unless there's any pressing question right now that I could answer. Otherwise, I'll switch off the recording, and Kai will stay online to continue to answer some questions. Maybe let me stop the screen sharing. Yes. So are there any very important questions that you want to ask me? If you want to ask them to Kai, just continue later on. Then apparently not. I turn off the recording.